Okay, these are your notes for section 4.5, and section 4.5 is about integrating by substitution. Okay, before we start talking about the theorem, remember when we were learning derivatives, and remember the worksheet we had that had the chocolate, you had your chocolate M&M and your peanut M&M? Okay, so I'm just going to talk about that just for a second. Here's an example, and we were finding derivatives of composite functions. If I had something like this, and you can just watch this, you don't have to write this down. And anytime we had to use the chain rule, we would use that sheet. This would be an example of just a plain M&M. Okay, my shell was this. My chocolate was what was inside. And remember what we did? We always found the derivative of this first, of my shell. So I would bring down my exponent, keep what's inside my parentheses, and then I would take the derivative of my chocolate, which in this case was 1. Okay, and then sometimes we would actually have a peanut M&M. Okay, and if we had a peanut M&M, it would look something like this: y equals, I don't know, sine 3x quantity squared. Okay, my shell was this, my chocolate was this, and then my peanut was that, and we found the derivative of each. Well, now we're going to have to find the antiderivative of composite functions. Okay, so anytime we're finding the antiderivative of a composite function, we're going to use substitution. Okay, I've written down theorem 4.13, and when you read through it, it's just not going to make a lot of sense to you. Okay, but I want you to look at this part right here. If I'm integrating f of u du, and what they've done is u is going to be some function on the inside. It was too much for them to write, so they're going to say, okay, instead of writing all of g of x, I'm going to use the variable u. So f of u, and then du stands for the derivative of u. So if I have a function with something u times the derivative of u, that's going to equal the antiderivative of u plus c because it's indefinite. All right, so the theorem may not make a lot of sense to you, so let's just start doing some examples. Okay, first of all, this is an indefinite integral because I don't have an upper and lower limit. So all indefinite integrals, I'm going to put a plus c at the end. I know I have to use substitution on this one, and here's why. First of all, I cannot simplify this by distributing my 2x. And the reason I can't do that is because it's all raised to a power. Now I could FOIL this out, then distribute my 2x, and then find the integral. Okay, that's just a lot of extra work. So the shortcut for this would be to use substitution. All right, so here's what we're going to do. We're going to say u equals. My u was my shell in my M&M, okay? So this right here is my u, what's inside my shell. U is x squared plus 1. Now, anytime I write down a u, I have to also write down the derivative of u, and that's what du will stand for. So the derivative of my u is 2x. Now, going back to the theorem that we just talked about, it said if I have u, if I substitute u in, I have to have the du next to it. And I do. It's right there. So I'm going to rewrite this problem as this right here is now u. I'm going to substitute u in, u squared. This 2x is my du. And I'm not going to write the dx anymore because I'm in terms of u instead of x's. So look at what we did. This right here is my u. This right here is my du. Now this becomes a very easy problem to solve. If I want to integrate this, I add 1 to the exponent, divide by my new exponent, plus c. Once I integrate, I can substitute my u back in. So my u was x squared plus 1 to the third over 3 plus c. And that's it. That's my answer. Now in the back of the book, they will write it like this. Same thing, right? I just always write it divided by 3. Okay? So we're going to use U-substitution. And my hint that I know I need to use U-substitution when I'm integrating is if I have something raised to a power, okay? If I have a square root or any kind of radical, that's a big sign I'm going to use U-substitution. So any times that we used chain rule for derivatives, okay, same rules apply for U-substitution. Anything to a power, any radical, things like that. So let's look at another example. Okay, this one is U-substitution because I have this 5x after my cosine. All right, so my u in this problem is going to be my 5x. And most of the time, if you're given a trig function to find the antiderivative, if it has anything other than an x after that trig function, that's going to be my u. Now remember, anytime I use u, I have to write du. The derivative of 5x is 5. So I have to check my problem. Do I have everything that I've written? Here's my u. This right here, there's my du. So that's a good thing. That's what we want. So now I'm going to rewrite the problem. I have the integral. I'm not going to write that 5 because that's du, and I'm going to write that down in a minute. Cosine, I'm not going to write 5x. I'm going to write u. And then I'm going to write du at the end. Okay, and it's just because even though that 5 was in the front, I always write my du at the end of the problem. Okay, so now we're going to integrate. The antiderivative of cosine is sine u plus c. After we integrate, we're going to substitute our u back in. Sine 5x plus c. Okay, let's do another one. Okay, my big hint here that I'm going to use U-substitution is I have something raised to a power, and I don't want to have to FOIL all that stuff out. So my u, most of the time, will be whatever's underneath the exponent. So x squared plus 10. Since I wrote down a u, I have to write down a du. The derivative of x squared plus 10 is 2x. So now I'm going to go back to my problem. Do I have everything I need? Here's my u. Here's my du. So now I'm going to rewrite the problem using u's and du's. Remember, we don't ever write the du first. We'll write that last. So I'm going to wait to write this. Instead of writing x squared plus 10, I'm going to say that's u to the 4th. And then I'm going to write my du at the end. Remember, we don't have to worry about my dx because now we're in terms of u. So now I'm ready to integrate. U to the 5th divided by 5 plus c. Now I'm ready to substitute my u back in. X squared plus 10 all raised to the 5th divided by 5 plus c. Okay, so far so good. All right, example 4. Okay, I know I'm going to use u substitution because I have something raised to a power, a quantity raised to a power. So u is x squared plus 1. So the derivative of my u, x squared, the derivative is 2x. So I need to go check and make sure I have everything. There's my u. I have a problem. I have only part of my du. I have the x, but I don't have the 2. So here's what we do. We can fix it. And the way we fix it is I can put a 2 in front of that x. But just like if I have an equation, I have to always keep things equal or the same. I can't start changing things. So if I multiply something by 2, which is what I've done, I need to multiply it by something that's not going to change the value of it. So for example, if I had the number 3, and I multiply that number by 2, okay, I can multiply by 2 as long as I also multiply by 1/2. because isn't 2 times 1/2 1? And I can multiply anything by 1 because it doesn't change the value. So here's the general rule. If you multiply it or if you add something to your du, you also have to put its reciprocal out in front because then I don't change the value of it. So I'm going to write a 1/2 in front. So now here's my new problem. 1/2 the integral. Here's my du, so I'm not going to write that yet. Here's my u squared, and now I write my du. So now let's integrate. My constant's going to stay out in front. Add 1 to the exponent, divide by the exponent, plus c. And then I always simplify this. That's u to the third. 2 times 3 is 6 plus c. And I'm going to substitute my u back in. My u is x squared plus 1 cubed over 6 plus c. That's quantity cubed. Okay, let's do another one. Okay, I know I'm going to use U-substitution because I see a radical sign. Okay, we know that we can rewrite this as 2x minus 1 to the 1/2. So I have a quantity raised to a power, so I know I'm going to use U-substitution. My u is 2x minus 1. So my du is 2. Okay, I have my u, I'm missing my du. So I can put a 2, but if I put a 2, I have to put a 1/2 out in front. Okay, so there's my u, there's my du. So I have 1/2. I'm not going to write my du first, I'm going to write it last. U to the 1/2 du. So now I'm going to integrate. 1/2 times, add 1 to the exponent. So 1/2 plus 1, or 1/2 plus 2/2 is 3/2, divided by my new exponent, but I don't want to divide by a fraction, so I'm going to multiply by its reciprocal. So now I'm going to simplify. My 2's cancel. Now do you see I have 1/3? So I have 1/3 u to the 3/2 plus c. And I'm going to substitute my u back in. 1/3 2x minus 1, that quantity raised to the 3/2 plus c. Last one. Okay, a big hint that I'm going to use U-substitution. I have a quantity raised to a power. So u equals 3x minus 1. The derivative of my u is 3. So I have to check and make sure I have everything. There's my u, and this time I do have my du. So I don't have to do anything. I just have to rewrite the problem. I'm not going to write my du first, I'll write it last. U to the 4th du. So now I'm going to integrate. U to the 5th over 5 plus c. Substitute your u back in. 3x minus 1, that quantity raised to the 5th plus c. Now today we're doing all indefinite integrals. Next week we'll do definite integrals using U-substitution. Okay, so your assignment for Monday is going to be on page 306. Okay, and I'll give you the problems on Monday. Have a great weekend.